Another application of this division is dealing with, upper dimensional concepts like, areas or volumes. And volume tends to be a pretty common one in Math 30, just because volume does involve three factors. So I would just like to talk about that. It talks about nested boxes. That truly doesn't matter, but it is the idea that we have some box. I'll make it a little bit three-dimensional, and they're telling me that the height is x plus 1. So I'll just put an h there, and then we know that we would have a base, and maybe I'll put width, length and width. It doesn't matter, right? It's pretty arbitrary. So what that allows me to say is that this volume function is the height times the base times the width, which logically, if we manipulate it, we get that the volume divided by the height is going to give me the base times the width. And that's a really important concept, because what I'm going to extend here is I'm going to say then that v of x, so the polynomial for volume, divided by the height, which was x plus 1, is going to give me the quotient, the result of the division. And I'm going to put q of x here, but I want to make sure that we understand that q of x in this context is some function that describes base times height. Now, I'm going to finish off the remainder, the division statement, by putting the remainder at x plus 1. If we do this correctly, there really shouldn't be a remainder, but you never really know until you actually do the division itself. So they've given us the volume function. It's x cubed plus 7x plus 14x plus 8. So what I'm going to do, I'm going to write it down here, that we are going to look to divide x cubed plus 7x squared plus 14x plus 8. And we're going to divide that by x plus 1. Now, I know we talked about earlier that you could rewrite that as x minus -1. That's useful when you're trying to do non-permissible values. Again, worth mentioning that x cannot be equal to -1 here. All right, remember that x is not a dimension itself. It's just a variable that would lead to give us dimensions. And if x is -1, the height of our box is 0, and therefore it doesn't have volume. So what I'm going to do is I'm going to just work through that long division technique again. So I'm going to take the leading term of v of x, x cubed, and divide it by the leading term of my divisor, which is x. X cubed divided by x gives me x squared. When I multiply that back onto the divisor, I have x cubed plus x squared, and I'm going to subtract that. That leaves me with 6x squared, because x cubed minus x cubed is 0. But I have to remember that the 14x and the positive 8 are still there, right? We just kind of rinse and repeat our technique. So 6x squared divided by x will give me 6x. When I multiply that back onto the divisor, I get 6x squared plus 6x. I'm going to subtract that. 6x squareds cancel. 14x minus 6x is 8x. And the positive 8 is still there. One last time, 8x divided by x is 8. When I multiply that back onto my divisor, I get 8x plus 8. And when I subtract those two expressions, I get 0. So we did get a remainder of 0, which is really, really important. And what I'm going to say now is I can say that v of x, and I am just going to cop out one last time and just write v of x, divided by x plus 1 is equal to x squared plus 6x plus 8. Now, because it wants an expression, right now that expression would be something that would give us the area of the bottom, right? So that is right now base times width. But that, x squared plus 6x plus 8, is very, very factorable. So if I factor that right-hand side, what I would get is x plus 4 times x plus 2. Now, I'm going to do one more thing here. I'm going to change this into the other division statement, which I can now say that the volume of my box is x plus 4 times x plus 2 multiplied by that height of x plus 1. And what we've done here is we've effectively factored this cubic, because v of x is x cubed plus 7x squared plus 14x plus 8. Well, we now know that can be written as x plus 4 times x plus 2 times x plus 1. And before you get too worried about, okay, how do I know what's the base and what's the width? The reality is it doesn't matter. If you have some kind of a cube or really a rectangular prism, because they wouldn't necessarily be the same dimensions, rotate it, and the base becomes the height or the width becomes the height. It truly doesn't make a difference. But really what we found is 3 different dimensions that when multiplied together give us the volume of the box. And that's a very useful concept, because if we knew we wanted to find the volume when x is 4, we could then find out using our factored form that if x is 4, then this box is 8 by 6 by 5. And I got those numbers just by putting x into each of those individual factors. All right, a very, very important application of this is that we can talk about, I'm just going to write the dimensions of the box. So the dimensions of my box, it is x plus 4 by x plus 2 by x plus 1. And that's typically how we give dimensions, because a three-dimensional object can be rotated and the base can become height. It just depends on how you're looking at it, right? A top-down view or a side view. Right, that's a really good example of one of the applications that typically does come up on the diploma, is the idea that volume can be written as the multiplication of three different factors.